Okay, so good morning again, everybody. And what I want to do today is a very important theorem that makes the connection between the topic of sequences, which was kind of a standalone topic which we've been discussing for the past few lectures, and functions, which are our main object of study in this course. And the theorem is the following. It's attributed to a mathematician called Highness, which is spelled like this, and it says the following. The limit of a function, f of x, as x approaches a, is L. So this is the good old notion of the limit of a function, with which we started off several weeks ago. If and only if, for any sequence, xn, I'm calling it xn rather than an, to indicate that it's a sequence of x's. It's going to live on the x-axis. For any sequence xn, which approaches a, this is a limit of a sequence. For any sequence xn which approaches a, and there's another little requirement that the xn's are not a themselves. For any sequence like this, when you take the sequence and plug it into the function, so you look at f at xn, so do you agree that this, if you fix a number, do f of it, do you agree that you get a y? You get something living on the y-axis, right? So f of xn is, you can call this yn. This is a sequence on the y-axis. Do you agree? This should approach L as n goes to infinity. So you have here the notion of a limit of a function in epsilon delta terminology, the way we defined it earlier. And this holds if and only if, and by saying it's if and only if, you can say that this is an equivalent definition. Okay? It's if and only if some phenomenon happens which is described in terms of limits of sequences. Okay? Do you see that? And let me draw the picture that goes along with this, and it's going to be the picture is really going to make sense. The picture is the following. So this is the x-axis, and this is the y-axis, and functions are blue. So here's f, and then there's the point A where I want to calculate the limit. Suppose it's this point. And then there's the value L, which is the limit, right? And in fact, to be consistent with everything we've been doing, I'm going to make a little hole here in the graph because we don't care about the value of the function at the point A itself. We are going to care about that in just a bit, but not right now. And the statement is the following. Saying that the limit is L, which I'm reminding you, for any epsilon, there exists a neighborhood here such that if the x's are close to A, their f's are close to L. Remember that definition? Everybody? Okay. Can alternatively be stated in terms of sequences in the following way. For every sequence of x's which approaches A, so you should look at my finger. I don't want to draw too much because it'll make it confusing. Think of a sequence of x's which get closer and closer to A. Not necessarily monotone. They can jump back and forth, but they get closer and closer to A. That's this statement, right? the value of f on these numbers is going to get closer and closer to L. Do you see that? For any sequence approaching A, the value of f on the elements of the sequence, which is a sequence here, approaches L. Is it convincing? Is it reasonable? Does it make sense? Good? Yeah.
I don't see why we need another. We have already a definition of the limit.
Good question. So the question was, okay, we have a definition of this, the good old epsilon delta definition. Why do we need another one or an equivalent one? Answer is, next board. I'm going to show you 3 different applications of this, 3 totally different situations where it's useful to use this rather than this. Okay? Since it's equivalent, it's not adding anything new to mathematics. The notion is the same notion. It requires proof, and I'm not going to prove it. The proof of Highness Theorem is really, it's confusing. It's confusing because it kind of blends the epsilon delta and epsilon n definitions of both sequences and functions, but it's very elementary. It doesn't use any theorems. It just uses the definitions. Let me show you how we use it, okay? And then that maybe will answer the question. So, examples or applications, if you want, of how we use it. So, the first example is going to be an example of, I'm going to give it a title, proving that a function does not have a limit. At some point. So this is the title of the first example. So consider the function f of x equals sine of 1 over x. We discussed this. Let me remind you what we had. We drew it, and we said that it looks like it's a sine of something, therefore it's bounded between -1 and 1. Does everybody remember this? Is this really a reminder? Okay. And it looks kind of like an accordion. When the x's get closer and closer to 0, it does all the back and forth waviness of the sign, but as we approach 0. So it looks like this. Right? And likewise on the other side, there's a big blur there at 0 because it's blurry. Okay? And so that's the graph of the function. And we said we didn't prove it formally using the epsilon delta definition, but we kind of argued the reasoning why this function does not have a limit at 0. And the reason we said was, okay, when you approach 0, let's say from the right, okay, you cannot find a small neighborhood of 0 such that all the values are going to be concentrated near some L. Because no matter how close to 0 you are, the values are always going to be all over the interval between 1 and -1 on the y-axis. Do you agree? That's the reasoning we gave. I want to now prove that this function does not have a limit at 0 using Highness Theorem. Okay, so this is the function. And the way I'm going to do it is the following. I'm going to give you 2 sequences on the x-axis. 2 sequences, both of which go to 0. 0 is our A, right? Okay, so we will show that the limit of sine of 1 over x as x approaches 0 does not exist. Do you know this abbreviation? Does not exist. And the way to show that is going to be the following. I'm going to show you two sequences, xn, and the other one maybe we'll call tn, both of which approach 0, which is our a. But when you do f of xn, you get one limit, and when you do f of tn, you get a different limit. And that is in contrast to the statement of Highness Theorem. Let's look again at Highness Theorem. Highness Theorem says, if you have a limit, take any sequence going to 0, our a is 0, when you plug it into f, you have to get the same limit. If I give you two sequences going to 0, one of which, when you plug into f, you get one limit, another of which you plug into f, you get a different limit, then this doesn't hold, and therefore this doesn't hold. Do you agree? So let's do that. Let's do that. So wait. So the first sequence is going to be the following. xn is going to be the sequence. Let me tell you first what it is, and then we'll find a formula for it. Folks, listen up here. I know this is intriguing, but listen up here and then ask questions, okay? So the first sequence I'm going to give is the sequence which on the x-axis is going to be the points where the function takes the value 1. So it's going to be this point. This is going to be x1. It's the first point where the value of the function is 1. Then the next one is going to be here. It's going to be x2. It's kind of small, but I hope you understand what I'm drawing. It's the second point where the function takes the value 1. And then there's going to be x3. It's in here somewhere. I don't want to write x3 because it'll blur everything. It's the third point where the function takes the value 1. Is it clear what I'm doing? So the xn's are going to be these points, and they can be calculated explicitly. Let me tell you what they are. They're 1 over 2n multiples of pi plus pi over 2. Why is this true? If you plug these values into sine of 1 over x, what do you get? You get 1 over this thing. 1 over this thing is just the denominator, right? And these are exactly the values where sine is 1. Right? Think of the sine wave, multiples of pi plus pi over 2. Right? Pi over 2, 2 pi plus pi over 2, 4 pi plus pi over 2. Yes?
Wouldn't that be going like the... Yeah.
Okay. So you should convince yourself. Okay, so let me write that in a second. So do you agree that this sequence is a sequence? It's never 0. It's never 0. But as n goes to infinity, its limit is 0. Because the only appearance of n is here. As n goes to infinity, 1 over this thing goes to 0. Do you agree? So that's the x's. It's this sequence of orange points on the x-axis which approaches 0. Okay? Now what happens when we look at f of xn? So f of xn, that's sine of 1 over xn, because that's the function. That's sine of 1 over this thing. 1 over is just sine of that. So it's sine of 2n pi plus pi over 2. Do you agree? Everybody?
Mm-hmm.
And these are precisely the points where sine is 1. So this is always 1 for any n, and therefore when n goes to infinity, it trivially converges to 1. So that's the first sequence. That's the orange points. Now I want to give another sequence. I want to stay on this board, so I'll write it up here. Let's call the other sequence, I used xn, and I don't want to call it yn, because that would be indicating somehow that they live on the y-axis. Let's call them tn. Tn is going to be the points. Let me draw them for you. Maybe let's take red. Tn is going to be those points where the function takes the value -1. So t1 is going to be here, where the value is -1. So this is going to be t1. And t2 is going to be here on the next occurrence of -1 is the value of the function. So this is going to be t2. And so on. I'm going to have this. And I'm sure it's hard to see because as we get closer and closer to 0, the picture becomes blurry. But I think the idea is clear. So what are those values? What are those values? Let's write. So the tn's are going to be 1 over 2n pi minus pi over 2. Again, this is a sequence which goes to 0 as n goes to infinity. And it's not. None of its elements is 0 itself. Right? And when you plug it into f, so let's erase this word here. F of tn is what? Is sine of 1 over tn, because that's the function. 1 over that is just the denominator, so it's sine of 2n pi 2n pi minus pi over 2. And these are precisely the values where sine is -1. And therefore, when n goes to infinity, it also goes to -1. Okay? So wrapping up the argument, what we did is the following. We constructed two sequences, xn and tn. Both live on the x-axis, for which one of them, when you plug into f, the limit is 1. The other, when you plug into f, the limit is -1. Different limits. Okay? Therefore, again, back to the theorem itself. For one sequence, the xn's goes to 0, but f of xn goes to 1. For the other, the tn's goes to 0, but f of tn goes to -1. Therefore, this doesn't hold. Not for every sequence that goes to 0, f of the sequence goes to the same L. And therefore, this doesn't hold. Questions? So either you're all in shock, or everybody understood. Or some people are in shock and the others understood. Yes? I cannot repeat the entire construction. So point me to where exactly you got confused.
Okay, so we were able to solve for the limits of f of xn and f of tn, and then after that you wanted to explain it based on the definition.
Right, not based on the definition, based on this theorem.
Yeah.
Okay, so we constructed two sequences which have different limits under f. That is in contrast to what this says. This says that for every sequence, f of it has the same limit L. So if we constructed two of them that have different limits, this doesn't hold. And if this doesn't hold, it's an if and only if theorem, then this doesn't hold. And that was the bottom line of this example. Maybe I didn't write that, so maybe let's write it here. Oh, I wrote it as we will show that, and we showed it. Okay, so let's add here. Let's call this fact star, the fact that the f of xn's go to 1, and let's call this fact star star, that f of the tn's goes to -1, and from star and star star, it follows that the limit of sine of 1 over x as x goes to 0 does not exist by Highness Theorem. Okay? Yes?
Is it like what we did last time? Sequences and subsequences? Is it a similar idea?
Well, it's related to sequences, but this is the first example of connecting sequences to functions.
Yeah.
Okay, so this is not a matter of a sequence and its subsequences. It's two different sequences, and it's relating it to functions using that theorem. Okay, this is a theorem that is usually harder to absorb. I know that. I know that from previous experience. It takes time to get used to, and you need the time. You need to practice more examples and to get used to it. Let me do another example and then more questions, okay? So here's another example. Example 2. Example 2. If you thought that was confusing, now wait for this one. Finding, so this is the title of the example, a limit of a sequence using functions. So what do I mean by that? So consider the limit I want to calculate is the following. Consider the limit as n goes to infinity, it's the limit of the sequence, n times sine of 1 over n. That's the limit I want to calculate. It's a limit of a sequence. Can we do it with the tools we already had? Not obvious. For example, this is bounded, but this does not go to 0. Right? The bounded times goes to 0 idea doesn't work here. We had something very similar. We had sine of n times 1 over n, and that's where we used bounded times goes to 0. Different idea, yes? Yeah.
Okay. We could define some t equals 1 over n.
Okay, so you're already trying to do what I want to do, which is resort to the function. Okay, that's what I'm going to do. But I'm asking, can we do it without resorting to the function? Okay, by previous tools, not obvious, not clear, right? So what I want to do is, I'm going to rewrite this. Do you agree that this is the same as the limit n goes to infinity, sine of 1 over n divided by 1 over n? Do you agree that this is exactly the same thing? Yes? Okay. We know that sine of x over x, this is a function, sine of x over x goes to 1 as x goes to 0. Does everybody remember that? That was one we worked pretty hard for, but it's useful. Okay? And what do we have here? We have sine of something over something, where that something goes to 0 as n goes to infinity. Do you agree? So we know this. Take xn to be the sequence 1 over n. This sequence is never 0, and its limit is 0. Do you agree? Now plug the sequence into the function. Plug the sequence into the function. Let's look back at the theorem a minute. Back at the theorem. The theorem says, and now I'm using its other direction, if we know that a limit exists, we know that limit of sine x over x is 1 when x goes to 0, then we know that take any sequence that goes to 0, plug it into the function, take the limit, that limit is going to be this L. The limit is going to be 1. That's exactly what I'm going to do there. I'm going to take the sequence 1 over n, it goes to 0. Plug it into the function, I'm going to get sine of 1 over n over 1 over n. Take the limit, the theorem tells me that limit is the same as the limit of the function. Let me write that. By Highness Theorem, when I plug the sequence into the function, f of xn, which is sine of 1 over n over 1 over n, that's f of xn, the limit of this thing, as n goes to infinity, is the limit of the function, 1. And that's the limit that I wanted to calculate. Clear? Questions? Yes?
Looks like you should, it's the same limit as you turn the sequence into a function.
So what do you mean it's the same limit as if I would turn the sequence into a function?
If you took in the first place and just change x to n to x and x goes to infinity, you have more than the same.
Then the problem was x goes to infinity, x sine of 1 over x. What would that limit be? Why? You would get x sine 1 over x as x goes to infinity. Right? Why is that?
See what's the use of this. You will just go to the limit in the right hand, and then you can calculate using what you learned before.
Okay, I understand what you're saying. You're using that same theorem. You're using that same theorem, but at a different place. So what you're suggesting is the following. Okay, so before I answer that, is what I did here clear? Did everybody understand what I did? Do you see why this is exactly using the theorem? Okay, so your suggestion was, instead of doing this, replace all these n's with x's. Just go to the function. How do you know that I can just go to the function and have the same limit? Why is that true? It's not just renaming the variable. This is looking only at the values on natural numbers. When you take the function, you're looking at the values on all real x's, right? So it could be that the sequence has a limit and the function doesn't. For example, if you look at something like, let's move to this board. If you can take, for example, a function that looks like, I can probably even come up with a formula, but it's not necessary. Look at the function which looks something like this. Take a cosine and multiply it such that it becomes, or a sine, such that it becomes, the amplitude grows and grows and grows and grows. Okay? Do you agree that this thing, well, the blue is a bit whitish, but do you agree, can you see it first of all? I'll try to bold it a bit. Okay, it gets bigger and bigger. Do you agree that this function does not have a limit at infinity? Right? And when x goes to infinity, this thing is completely untamed. Do you agree? But if you look at the values on the natural numbers, the sequence just of the values on the natural numbers, if I set it up correctly, it could be, for example, this sequence, which goes to infinity. Or maybe if I set it up correctly, I could get just the values here. And the values could be 0. If I look just at these values, depends on what formula I give and how it sits on the natural numbers. Do you agree? So it's not obvious that when you have a limit of a function and you look at the values of that function on the natural numbers, you'd get the same thing. Okay? Highness theorem tells you when that would happen. If the function has a limit, then any sequence you would look at the values on, as long as the sequence approaches the direction in which you're doing a limit, and I gave the version for x goes to a, you can give an analogous version of Highness theorem for x goes to infinity. If the function has a limit, any sequence, plug it into the function, it would have the same limit. That's Highness theorem, and that's what you would be doing by changing this into x's. You would say, okay, let's look at the function. The function would now be x goes to infinity sine 1 over x over 1 over x. This I know is 0 because it's related to this, change a variable or whatever. Therefore, by Highness theorem, any sequence would also have the limit 1. Do you agree? Okay, so that was a very important observation, but it's still using Highness. It's still not a trivial fact that a sequence and a function, you just change the variable and they behave the same. That's not at all a necessity. Yes?
So can we say that L in Highness theorem can be infinity?
Yeah, that's what I mentioned, that I gave a version of Highness theorem for x goes to a. You can give a version of Highness theorem for x goes to a plus, or x goes to a minus, or x goes to infinity, or x goes to minus infinity. And L can be infinity, I assume, yes. Okay. Maybe some things I have to think about more carefully, but in general, this theorem is just redefining limits in terms of sequences, and it should work everywhere. Okay. Let me do one more example and then take a couple more questions. Okay. So, did everybody understand what I was drawing here? Why I drew this thing? Is this idea clear? So this is something to keep in mind, that the behavior of a function, when a sequence, we mentioned that. We mentioned that a sequence is a function only on the natural numbers. And the behavior only on the natural numbers can be very not related to the behavior of the entire function. That's what this picture wants to indicate. Let me take more questions after the next example. Okay, so another example of using Highness theorem. So example number 3. Proving theorems, for example, for functions, based on theorems for sequences. So I want to show you an example of, suppose we know a certain theorem for sequences, and I want to state and prove the equivalent theorem for functions, and we've seen that the theorems are very similar, right? You have arithmetics for sequences, you have arithmetics for functions. You have sandwich for theorems, sandwich for functions, right? I want to show you how by Highness theorem we can bridge and prove one based on the other. So, suppose we know the following theorem: if an goes to 0 and bn is bounded, then an bn goes to 0. This is a theorem for sequences. Okay? If you want to formally prove it, you prove it off either the definition of the limit for sequences, or I think we mentioned this can be proved using sandwich. I think we did that, or I don't remember even which one we did. Maybe we proved the function one, but it doesn't matter. Okay? So this, suppose we know it. Suppose we proved it. Okay? So suppose we know this. Let's prove the following statement. If f of x goes to 0 as x approaches some a, and g of x is bounded, then f of x times g of x goes to 0 as x approaches a. This is its counterpart in functions. Do you agree? Okay? Do you agree that these theorems are buddies? Okay? So suppose I know this one, I want to prove this one. How do I do it? So here we go. My black is dying, so let's say goodbye nicely. Take a new black. Okay. So proof. Since f of x goes to 0 as x goes to a, this is given. This is the data of this theorem. This is what we're proving, right? So we know this. Do you agree? Say yes. Okay. Therefore, and here I'm going to use Highness Theorem. Highness. For every sequence that goes to A, f of the sequence goes to 0. Do you agree to that? That's what Highness Theorem tells me. And I'm using L equals 0 because that's the situation. Right? Okay. Therefore, if I look at f of xn times g of xn, what can I say about this? F of xn goes to 0. Here it's as n goes to infinity, right? These are sequences. Do you agree that f of xn goes to 0? What do I know about g of xn? It's bounded. It's a bounded what? Sequence. Xn is a sequence. G is a function. G of xn is a new sequence on the y-axis. G of x1 is the first element. G of x2 is the second element. G of x3 is the third element. And since G is a bounded function, that's the assumption, the other assumption of what we're trying to prove, G of the sequence is bounded. It's a bounded sequence. Do you agree? Confusing. It's a bit confusing, but so this goes to 0 as n goes to 0 to infinity. And this thing, this is a bounded sequence because G is bounded. Since G is a bounded function. Do you agree? Okay, yes?
I understand that intuitively, that g of x is a bounded sequence because g is a bounded function, but that's not an application of Highness, right?
Not, well, we used Heine to say this.
But not for g of x.
No, so far we didn't say about anything about this. We just argued to facts. The fact that this is a bounded sequence follows from the fact that G is a bounded function, not related to Heine, and we know this because this is the data of what we're trying to prove. Okay?
Need to prove that the relation can't.
Wait, I'm not done. Wait. Wait a second. So, what can I say about the limit of the product? This is a sequence that goes to 0 times a bounded sequence. 0. Why?
Because we have this theorem for sequences.
Right. I'm assuming that I know the theorem for sequences. So this is now AN, this is BN, and this is this theorem. So therefore, this follows by theorem star. This is the theorem we assume we know.
But what do we choose for xn?
For any xn. For any xn. So this is true. I should even emphasize this. So therefore, for any xn which goes to A, this goes to 0. Okay? Good. And now I claim that now we can wrap up and say this. This is what we want to show, remember? We want to show that f times g goes to 0 as x goes to A. What we showed so far is that for any sequence that goes to A, f times g of the sequence goes to 0. So now use Highness again in the second direction. If for any sequence, f times g of the sequence goes to 0, by Highness, other direction, f times g goes to 0. Okay? So, let's write that. Ooh, running out of board. Let's erase this. And continue up here. Therefore, and this is again using Highness, but the other direction now. Now I know the right-hand side of Highness, and that implies the left-hand side. So for any sequence this holds, therefore it holds for the function. And that completes the proof. It looks pretty redundant. I agree that we're using, well, it's proving a theorem which is analogous to a different theorem. That's why it may look redundant. But if you look line by line what we did here, we proved this knowing only this and Highness theorem. Okay? Now, all three applications that I just gave are not easy. Okay, they take this the use of this theorem, and this is already takes some, I don't know, some you have to be already prepared to do things like this. That's why it shows up at the end of the discussion of limits of sequences and limits of functions and so on. You have to think about it. You have to read these examples again, and you'll, of course, get practice things of all of these forms. I think of all of these, the most useful one for you, proving things like this is very useful, but we're not doing that many proofs in this course. But for you, I think the most useful one is proving that limits don't exist. Proving that a limit doesn't exist using the epsilon delta definition is oftentimes tricky. And proving it using sequences is very often not hard. You just find two sequences which under f have different limits. That's it. F doesn't have a limit. Okay? Okay. So let's take a break. After the break, promo for after the break, what I want to do after the break is look at this picture. This was just the picture of the limit phenomenon. And take into account this point, which so far was the only thing we didn't care about. Okay? And that's going to be the notion of continuity after the break.